Hello. This is going to be a quick introduction video to the rest of the series I'm going to make. So my goal for this series is to go through the definitions and the basic ideas that underlie all of the most fundamental fields or topics in math and all the way back into logic. We have sort of complicated ideas like vector spaces and algebras like Clifford algebras and Lie algebras, and these are built on things like fields. Lie algebras specifically relate to these things called groups, and then these fields and groups are defined based upon sets. So these definitions of things like fields and groups assume that you already know what a set is, and they inherit all of the properties of sets, the axioms that define what they are, and all of the theorems. And so as we go up this ladder, we're kind of just adding properties or structure to the thing below. And it turns out that just about everything in math is built on sets, or you can at least trace back their construction to a set. And then set theory finds its roots directly in logic. Algebras, their definition is just a vector space with some additional properties. And then a vector space is a set over a field. And a field is basically like a set that forms two groups. And a group is a set with some operations that you can do to the elements. And the axioms of set theory are very tightly intertwined with the axioms of logic. And so in the first few videos, I'm going to build a little bit of foundation in logic, and then in the second and third video, you'll see how those axioms of logic sort of morph into the axioms of set theory. And then from there, we'll go up through this ladder, through math, until we get to algebras. So I just want to share a little bit about me real quick. When I was in middle school and high school, I really didn't care about, well, like anything, but especially not math. But then after high school, when I really had to think about what I wanted to do with my life, I realized that I had always been really interested in physics. And I thought, hey, I think it would be really cool to do something in science, maybe with physics. But in order to do physics, you really need to be decent at math. You don't have to be great, but physics is math. So I majored in astrophysics, and I eventually decided I would major in math too, because I wanted to take more math classes in order to just get better at math. But I had already taken a few math classes at a community college, so I figured I would just take a few more math classes in college. So that's what I did, and to be honest, those math classes were really hard. And looking back, after the fact, I realized that it was because I didn't really learn any math in middle school and high school. So even though I knew how to do a little bit of calculus, I didn't really understand the foundation of what I was doing at all. Like, okay, what is an integral? Okay, but you can define an integral the way that they do in, say, Calc 2. But that definition assumes that you know what a few things are, and ideally you know the definitions of those things as well, so that you can then apply that deeper background knowledge to calculations and derivations and proofs in this higher level thing. So for instance, if you wanted to prove something about integrals, well, integrals are operations that you do on functions. Using integrals requires you to know what a function is. So if you don't really understand the definition of a function, it's going to be pretty hard to prove things about integrals. Just like in the same way, if you want to prove something about vector spaces, well, it's really going to help if you know what a set is and what a field is, but not just what they are in an abstract sense, but what they are in a very literal, technical, specific sense. What are the axioms? What are some of the theorems about them? And so I really didn't have that background. And that's what led me to learn all of this stuff that I'm going to share with you in this series. Back in the ancient Greek times, Plato came up with this idea that there was a realm, a dimension of perfect forms. And this realm is where the pure geometric figures existed. That is, perfect squares, triangles, circles, cubes, anything you can think of. In our universe, nothing is perfect. There is no perfect square. At least not in the sense of, like, this square here. That square does not exist as a physical object in the universe. But Plato believed that these objects existed in this other sort of parallel universe. And these days, it is common to think of this realm of perfect forms as sort of the world of math. Because if you think about it, even if we move away from geometry and into functions, differential equations, derivatives, all these things, none of these things exist in our physical universe. They describe our physical universe, but then even that description is an idealized description. No movement or interaction is going to follow the expectation of a simple equation. It can be very close, but it's not exact. Quantum mechanics is the most accurate theory we have ever come up with, where the equations of quantum mechanics give predictions to experiments, and those predictions, the numbers that we get, fit the results of the experiment very closely. So when you do a calculation to see what the result of an experiment is going to be, and the equation spits out a number, and then you actually do the experiment, the number you get from the experiment matches the number you get from the equation, from the calculation, better than equations in any other physics theory. The numbers we get from the equations match the numbers we get from the experiments, oftentimes out to 10 or 20, even 30 decimal places. But it's not exact. Eventually, the numbers diverge. So our mathematical calculations using equations, even very complicated equations, never match what's actually happening in reality exactly. So the idea is that math lives in this other world. I like to imagine an infinite expanse of sky with just cubes and pyramids and squares floating around. So now in this introduction video, I just want to cover a couple of things that are part of logic but sort of lie outside of the axioms of the first three fields of logic that we're going to talk about in the coming videos, because they're just so fundamental. They do in some ways show up in the axioms, but they mostly actually lie behind the axioms a little bit, or below the axioms. They're even more fundamental. So there are a couple things I want to mention that I think are really important if you want to have a basic understanding of the foundation of logic. And the first thing is the three laws of logic. Now, what are the three laws of logic? Well, the first law is called the law of identity. Now, I'm going to use some symbols here that I'll actually explain in the next video, but I thought it was important to cover these three laws because they're not really going to come up again. They're just so fundamental that if we really want to start exploring logic and math, we immediately move past these three laws. So how we represent the law of identity in logic using logical notation is like this. Now, the law of identity just says that any logical statement, which we call A, it could be the sun is shining right now, or that ball is red. Any logical statement like that implies itself. That's what the arrow is. That's an implication. It's if then. So if A, then A. So if that ball is red, then that ball is red. Pretty simple, right? The second law is called the law of non-contradiction. And the law of non-contradiction is written like this. So what does that say? That says not, this is not, or negation, So, for instance, if A is true, then not A is false. And again, we'll talk about that in the next video. So I encourage you to come back to this after watching the next video and thinking about it again. But basically what this says is, if you look inside the parentheses, we have A and not A. And this little caret here, this wedge, means and. So we have A and not A. And this is saying you cannot have that. You cannot have A and not A. So if A is true, A and not A is saying that A is true and false. And non-contradiction says that you cannot have a logical statement, A, which is both true and false. And the third law is called the law of excluded middle. And this one is written not A or A. What middle are we excluding? We're excluding the possibility that true and false exists on a spectrum. With true on one end and false on the other, we're saying that if true is this endpoint and false is this endpoint, we are excluding the middle between them. So a statement A must be either true or false. And as you've probably figured out, this upside down wedge means or. Now, as we'll see again in the next video, when you say A or B, this whole thing is true if A is true or if B is true. But if both A and B are true, then this whole thing is still true. Because if A and B are true, then A or B is true. So excluded middle does not say that A can only be one or the other, true or false. It just says that it can't be anything in between. It has to be true or false. You can see how it's very important that we have non-contradiction, because that's the one that says A must be true or false, because it says that you cannot have both. But the law of non-contradiction by itself just says you can't have A and B. So if we only had non-contradiction, we could have that the statement A was neither true nor false. Because if it was neither true nor false, this would be satisfied. If it's neither, then it's not both. And so sit with that for a moment and just appreciate how we really need the combination of these two in order to enforce the rules that would give us a logic that makes sense. Consider the implications of not having these. We could have a statement that was true and false. We could have a statement that was neither true nor false. We could have a statement that was kind of true, kind of false. Which, when we're just talking in everyday language about regular things, there are definitely statements that can fit into those categories. That could be neither true nor false, or both, or a little bit of both. Like the statement, I'm feeling sad. That could be a little true, a little false. And so there are fields of logic whose axioms do not satisfy number 2 or number 3. I haven't come across one that doesn't satisfy number 1, but there are definitely some that do not satisfy 2 or 3, or they don't satisfy either sometimes. They go by names like dialectical logic, para-consistent logic, and dialectical logic that has to do with speaking. So that system of logic is more philosophical and has to do with actual everyday communication with language, how we talk to each other. But if we want to be very, very precise and accurate and rigorous, that is, if we want to do math, we need our math to be built on a system of logic that satisfies all of them. And in logic, a set of axioms that satisfies all 3 laws is called classical logic. So the axiom systems that we'll look at in the next few videos describe logical systems that fall within classical logic. So I guess I'll just list them here. So the next 3 videos are going to be on propositional logic, first order logic, and second order logic. These all fall within classical logic, and they all satisfy the 3 laws. So now, one final topic that I want to talk about is actually just a couple of definitions. We have axioms. I've been saying this word. What really is an axiom? And a set of axioms. A set of axioms is basically a definition for an entire field of logic or math or philosophy or physics or anything really. So a set of axioms are not proven. They are assumed to be true. So it's usually a short list of logical statements that are assumed to be true. You do not prove them to be true. They are either assumed to be logically obvious, or they function more like a traditional definition, like a definition in a dictionary, where they say this mathematical object exists, like a group or an algebra. It exists and it has this list of properties. And that's not something that you can prove. It's something that we sort of came up with. We created it. Groups, fields, all of these things, we sort of created them. And how did we create them? Axioms. Or you can very accurately think of axioms as just definitions. So you're laying the groundwork, you're defining this is what this thing is, and then from that set of axioms, or this list of properties, we can prove theorems. And theorems are the things that are useful. The fundamental theorem of algebra, or the fundamental theorem of calculus, or Maxwell's equations can be thought of as a theorem. It was something that had to be proven. So theorems are really the things that we use in math. They're the things that let us do the interesting and cool things. And so a theorem is a statement that is proven from the axioms. And now if you think about it, this kind of gets to that philosophical question of whether or not math is discovered or invented. It's sort of a combination of both. In a way, we sort of create axioms, and we choose the set of axioms and kind of construct them in a way that we can see that they will eventually be useful. And when I say eventually, I mean once we prove some theorems, and then with those theorems prove some further theorems, we build up the structure, and we can see that eventually, if we construct the axioms this particular way, they'll eventually lead to useful results that describe reality. And so the axioms are sort of constructed, but the theorems are then discovered. And we can see, as we're constructing them, the results that they'll lead to, the theorems that they'll lead to. And we want to find theorems that are interesting and that describe reality. And so then over time, we can refine the axioms to get them to lead to theorems that are useful. It's not really true or false that a vector space exists or that vector spaces exist. That's not really something that is inherently true or false. Using axioms, we define a vector space and its properties, and those are the axioms of the theory of vector spaces. And then that leads to all the theorems of linear algebra, just those axioms. And all of the cool and useful stuff that we do in linear algebra is necessarily true if those axioms are true. And so the axioms are sort of constructed by us. We say these things are true, a vector space exists, and it has these properties, and then we discover those theorems that were always true. So my point is that the axioms are constructed and the theorems are discovered. Now, if we expand on this idea a little bit, we can discover something really interesting. So again, I have two definitions I want to show you. The first definition is consistent. So it's a very simple definition. If you have a set of axioms, a collection of a few definitions, it can be called a consistent set of axioms if it does not lead to contradictions. So what does that mean? That means the axioms cannot prove a statement true and false. That's pretty simple, right? So the axioms must prove a statement A to be either true or false. If you can prove its truth, it's got to be either true or false, not both. If you could prove a statement true and false using the axioms, then that system of axioms leads to contradictions, and it is not consistent. Okay, the other word is complete. A set of axioms is complete if it can prove all statements or theorems that are logically implied by the axioms. So you remember how I said that once you've established a set of axioms, there are all of these theorems that are logically true given those axioms, and mathematicians work to discover those theorems. But there's all these theorems, perhaps an infinite number of theorems, that are necessarily logically true if we take the axioms to be true. So once you start with, say, the definition of a vector space and its properties, all of the things in linear algebra were already true, but it took time to go from those axioms, from that definition of a vector space, and discover all of the things that you can do with them. It isn't just immediately obvious. It sometimes takes hundreds of years for mathematicians to build up a field of math from a definition and properties. But just because mathematicians haven't discovered the theorem yet doesn't mean that the theorem isn't true. It must be true. It's logic. We're using logic to reach out into this world of perfect forms that we can't see, but we can kind of feel with our minds. And we reach out into that realm of perfect forms and slowly feel around and discover what's there. So it's like, I don't know, think of like Minecraft. Say the realm of perfect forms is like the under the ground in Minecraft, and you can go dig down in there, but you can't see anything at all. But discovering a system of axioms that is consistent and which satisfies the laws of logic is like digging down in the ground in Minecraft and discovering a big open cave. And then you have to go and explore the cave. The cave is dark. You have to set lights around. That's like discovering theorems, is like placing a torch so you can see the surrounding area. And you go out and you explore and you find what's in that cave. You find all the theorems. And so this guy, Gödel, discovered some theorems. They're called Gödel's incompleteness theorems. There's the first incompleteness theorem and the second. And what the incompleteness theorems say is that any set of axioms that is logically consistent and which can describe math is not complete. So what that means is that any field of math with its set of defining axioms or properties has essentially theorems out there in that cave. They're there, but you can't ever find them. You cannot prove. There will always be some theorems that are true, but you can't prove them. So if you think about it, there are theorems in math that are true that we will never know about. The second incompleteness theorem says that if you look at any of those axiom systems that is consistent and can describe math, and as we know now is not complete, that axiom system, since it is not complete, cannot prove all of the true things. And one of the true things that it cannot prove is that it is consistent. So to summarize, Gödel's incompleteness theorems say that any system of axioms that does not lead to contradictions and which can describe math has theorems that it cannot prove. And one of those things that it cannot prove is that it does not lead to contradictions. So that's going to wrap up my video. Hope to see you back here for the next one, where we're going to go into propositional logic and really start this exploration of logic and math. Thanks for watching. If you found this video interesting, please click like, maybe even subscribe, and if you have any questions, any future topics you want to see, please leave a comment. Thank you.